Good morning, everyone, and welcome to your final Happy Math Hour of the semester and of the year. I want to congratulate everyone for making it to the finish line and, give yourself a pat on the back, for making it this far. Um, Today, we're going to have the final exam review for both 1314 and 1324. If you are here for 1324, please click on the link to the Math 1324 room in the chat. And without further ado, I leave you with Mr. Ruben Carrizales, Albert Isasi, and Ms. Yvette Chuca. Thank you.
Good morning, everyone. And again, thank you for joining us on our last session of the Friday Happy Math Hour. I'm sure all of you are going to do excellent on your finals. As mentioned, we're almost on the finish line. Let's go ahead and get started. Okay. All right. So, again, we're doing a review and we'll try to catch a little bit of everything that we saw in the semester. So, let's start with this question here. It says, find any intercepts and test for symmetry with respect to both axis and the origin. So, the equation here is y is equal to negative 2x plus 1. So, let's find the x-intercepts, y-intercepts, and then we'll check for symmetry. So, again, if you recall, to find the x-intercepts, we would set y equals to 0, and then we would solve for x. So once we do this, we have 0 is equal to minus 2x plus 1. Solve for x, and we get that x is equal to 1/2. Yes? So that is our first answer here. Our x-intercept, when y was 0, x was 1/2, and we put the answer as an ordered pair. Um, just be careful. Don't do what I did here when I plug it in the problem. The computer will mark it wrong. Okay, don't put the double parentheses. The computer's already giving us the parentheses, so don't do double parentheses. I just noticed that. Okay. All right. Now, if I want to find the y-intercept, again, what I want to do is I'm going to set now x equal to 0 and then solve for y. So let's go ahead and do that. So here we would set x equal to 0 and solve for y. So we have y is equal to a negative 2 times 0 plus 1. Um, and this is going to give us y equals 1. So again, when x equals 0, y equals 1 as an ordered pair is a 0, 1. This is my y-intercept. Okay. So now let's check for symmetry. So if I were to graph this, okay, I can see that my graph doesn't have any symmetry. Okay, it's a line, but let's go ahead and go through the process on how to determine for symmetry. Okay, so when you're checking for x-axis symmetry, what you want to do is you want to replace the value for y with a negative, and if that gives you still the same equation, then it has that axis of symmetry. So let's go ahead and do the check for x-axis symmetry first. So again, my equation is equal to y is equal to negative 2x plus 1. And I'm going to replace y with negative 1 and solve again for y. Okay, so when I do this, I replace the y with a negative y and I solve for y again. I have this equation, y is equal to 2x minus 1, which is not the same equation that I had started with. My original equation is minus 2x plus 1. So since this didn't result in the same equation, it has no x-axis symmetry. So now similarly, to check for the y-axis symmetry, instead of the y, I'm going to replace the x with a negative x. Okay, so then I'm going to do the same thing. I have y is equal to minus 2x plus 1, and I'm going to replace the x with a negative 1. And when I do this, I have this equation, y is equal to 2x plus 1, which again is still not the same equation. Okay, and then the last one to check for the origin, um, for symmetry on the origin, I'm going to replace both the x and the y with a negative. Okay, so again, my equation is y is equal to minus 2x plus 1. Let me go ahead and replace both the x and y with a negative. And when I solve for y again, I get y is equal to minus 2x minus 1. Again, we come close, but it's not the same. So hence, since none of these gave me back my original equation, this equation does not have symmetry. Okay? All right. So let's move on to finding the standard form of the equation of a circle. Okay, so in this particular problem, they give us characteristics of the circle. They tell us that the center is at negative 4, 2, and the radius is 2. So let's recall the format for the standard form of a circle, which is given by this: x minus h squared plus y minus k squared is equal to r squared, where the center is given by the h and k, and my radius is the variable r. Okay, so here in my case, h and k is given by negative 4, 2. They tell me that my radius is 2. Let's just plug it into the equation and simplify. Okay, everywhere I saw h, I plugged in the negative 4. The k was a positive 2, and the r was a 2. When I simplify, I'm going to get x plus 4 squared plus y minus 2 squared is equal to 4. And that is my answer. Okay? All right. Let's try this different equation. Or this different question, excuse me. It says, write equations of the lines through the given point parallel and perpendicular to the given line. Okay. And I just noticed something about myself. I want to try to give you everything to get you ready for your final. But if I am going a little too fast, please let me know. You can unmute yourselves, raise your hand, and just let me know that I'm going too fast. Also, just be aware that you are able to download my presentation with a little box and arrow on the top. And again, you are all familiar with all this already. Okay, so they give me this equation, 8x minus 2y is equal to 3, that I have to find another equation that is parallel to this line and also perpendicular to this line. But not only that, it has to go through this point. It has to go through the point 8, 1. Okay, so the first thing that I need is, in order for me to find out if a line is parallel and perpendicular, is determined by its slope. Okay, so what I'll do first is I'm going to find the slope of this given equation that they gave me. And to do that, I'm just going to convert it from general form to its slope-intercept form. And that means solving for y. So when I do this, when I get 8x minus 2y equals 3, and I solve for y on this one, I get y is equal to negative 3 halves plus 4x. Okay, so the only piece of information that I'm interested in is in this part, the 4 here, with that it's multiplied to the x. This 4 is representing my slope. Okay, so to get a parallel line that is parallel to this given line, that line has to have a slope of 4 with a different y-intercept. So let's go ahead and do that. So to do this, I'm going to use my point slope formula. Okay, my point slope formula is given by y minus y1 equals m times x minus x1, where x1 and y1 is a point in particular that I want my line to go through. And that's the reason why I'm using this equation, because they told me that they wanted me to go through this point 8, 1. Okay, so let me substitute. I have everything to solve. Let me just plug in everything that I know. Okay, so y minus the y1 is a positive 1. My slope is 4. And again, my x is 8. Okay, let me go ahead and distribute the 4. And when I do this, I have y minus 1 is equal to 4x minus 32. Okay, let me go ahead and um, add 1 on both sides, because that's the last process I need is solve for y. So when I do this, I get y is equal to 4x minus 32 plus 1. And when I combine my like terms, I get, I get y equals 4x minus 31. So this is my answer that is parallel to this line. And again, because it has the same slope. So it has a 4. And again, if you recall, my original problem had a different slope other than negative 31. Okay. Now, to find the perpendicular slope, what I need to do is find the a perpendicular equation. I need to find the perpendicular slope, and the way I do that is it's getting the negative reciprocal of the given slope. So that what's going to give me the perpendicular slope. So the negative reciprocal of 4 is 1 over 4. That's the reciprocal. And what I do is I change the sign, okay? Because they're opposites of each other. Parallel and perpendicular are opposites. So if my parallel was positive, then my perpendicular has to be negative, okay? So this is my perpendicular slope, negative 1 over 4. I'm going to use my point slope formula again to come up with the equation that goes through this point, 8, 1. So let's plug in everything that was given to us. First, we're going to distribute the negative 1/4 to the x and then to the negative 8. Um, let's simplify. When we simplify, we get y minus 1 is equal to negative 1/4 x plus 2. The last step is to add 1 on both sides. And I combine my two like terms. 2 plus 1 is 3. And now this gives me my answer. This is this equation of this line, y equals negative 1/4 x plus 3 is perpendicular to the given line that they gave me, and it goes to the point 8, 1. Okay, excellent. All right, let's do these other equations. Let's do basic operations with functions. So they're giving me two functions that have a red, and red here is function f of x, which is 9x plus 1. I have a function here in blue, which is called g of x. It's x squared minus 4. And they want me to do basic operations with it. So for the first one, A, they want me to do f plus g of x. That's how I read this. But basically what they want me to really do is add f with function g. So what I do is I like to rewrite it so I can just substitute. Okay, I like to rewrite f plus g of x into what they want me to do. They want me to do f of x plus g of x. So now all I have to do is replace these with what they're giving me. Again, the red one was the f of x, which is 9x plus 1. And I'm going to add it to the blue one, the g of x, which is x squared minus 4. Now all I have to do is combine my like terms. I have only an x squared. I have only a 9x, but I have two constant terms that are like terms. The plus 1 minus 4 is going to give me the minus 3. And this is my solution for f plus g of x. All right, let's do B. Now they want me to subtract. They want me to do f minus g of x, meaning they want me to subtract function f with function g. Okay, so all I have to do is substitute. Replace f of x with 9x plus 1, which is the red one. And the subtraction, since I have a subtraction, I know I'm going to have to do a distribution property. So I put parentheses for my g of x, which is x squared minus 4. So the first thing that I needed to do is distribute that negative both to the x squared and to the negative 4, which is going to give me the negative x squared plus 4. Now it's just combining like terms again. I only have my constant terms that are like terms. So we have plus 1 plus 4 is going to give me the 5. So my final answer is minus x squared plus 9x plus 5. Okay. Then let's do C. What they want me to do is fg of x. What they're really telling me is they want me to multiply function f with function g. So let me rewrite this as what they want me to do. They want me to multiply f of x with g of x. So I have them here. The red one was 9x plus 1 is f. The x squared minus 4 is the function g. And to simplify this, we're going to do FOIL. The 9x needs to be multiplied to the x squared, needs to be multiplied to the negative 4, which gives me 9x cubed minus 36x. Now I need to multiply the 1 to the x squared, the 1 to the negative 4, which is going to give me the x squared minus 4. Then I combine like terms if I can, and I can't. None of these are like terms. I could have left this answer like this for the computer, but I like to put it in descending order, which is just normal for me. And you don't have to do this. So the final answer is 9x cubed plus x squared minus 36x minus 4. Okay, and let's do the last one, D. They want me to do f divided by g of x. So what they're asking me is to divide function f with function g. So I rewrite this from what they want me to do. F of x divided by g of x. Again, substitute these functions. F of x is the red one, 9x plus 1. G of x is the blue one, the x squared minus 4. And I would simplify if I could, but in this case, I cannot simplify. Okay, I cannot remove an x because this one is being added with a 1. This x is a squared subtracted from a 4, cannot do anything with it. This is my final answer, 9x plus 1 over x squared minus 4. Now, you may be asked also to find the domain of this particular one. And why do they ask us only on this one? Is because we have a fraction or a rational expression that we never want the denominator to become zero, because if that happens, we have an undefined equation. So that's how we guarantee that we don't use something that's going to give us an error or an undefined equation. So let's find the domain. And to do that, to find the domain of this function, is I'm going to set the denominator equal to 0. Okay, so the denominator is x squared minus 4, and I'm going to set it equal to 0. And if I find an x value that will give this statement a true statement, okay, that's my restriction on my domain. Hence, it's going to be my um, my domain in interval notation, excuse me. So here, I have x squared minus 4. So one way I can do it is I add 4 on both sides, take the square root of both sides, and I end up that x is equal to plus or minus 2. That means that if I were to use a positive 2 or a negative 2 here for the denominator, I would get a 0. So these two values are my restriction. I cannot use them. And if I do use them, I'm going to get an error, undefined, right? So how do I write these two values as an interval notation? So here we have from negative infinity to negative 2, union from negative 2 to 2, and then union again from 2 to infinity. Okay, now these we're using parentheses because parentheses tell us that these are the numbers that we're stopping by, but we're not going to use them. Okay, so this is this question. Okay, all right, so one of the questions that you may be asked is if a function has an inverse. So let's kind of also review what a function is too, right? A function is defined by 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 having a graph or an equation that for every x value corresponds to only one y value. And there's a test that we can perform to find if a graph is a function. And this test is called the vertical line test. So the what you do is you take out your pencil or you do an imaginary vertical line and you move it across the graph. And this imaginary or your pencil, this vertical line, crosses the graph only once, then the graph is a representation of a function. Now, how do we find if it has an inverse? Well, we do the opposite of operation. To find if a graph has an inverse function, instead of a vertical line, we perform is a horizontal line test. So on this particular problem, okay, to find out if it has an inverse, we would do the horizontal line test. Again, I would take out my pencil or an imaginary horizontal line, and I would go up and down the graph, okay? And if my imaginary horizontal line crosses my graph only once, then this graph has an inverse, okay? And what I'm testing is, again, when I was testing for a function, every x value corresponds to only one value. Now I'm doing the opposite. I'm checking that every y value corresponds to only one x value. Okay. All right. So let's find these inverse, or let's solve for this. Determine whether this function has an inverse. So first of all, we have this function f of x is equal to the square root of x minus 8. Okay, so what we want to do is we can perform the vertical line test, and when we do this, we know that it's going to pass it. My imaginary vertical line is only going to cross my graph only once, and if I do my horizontal line test, it's going to tell me that it does have a um, inverse. Okay, so this has an inverse, and when it passes these two tests, we say that this function is one to one. So you're going to hear that word. Sometimes for your test, they'll say this function is a one to one. Find its inverse. So when they tell you that, it's telling you that it already passed these two tests, so it does have an inverse. So let's go ahead and find the inverse for this function. Okay, so to find the inverse, what I'm going to do is first convert this function back to an equation. And I do that easily by replacing the f of x with y. Okay, so I have y is equal to the square root of x minus 8. Then I'm gonna interchange or swap my x's with my y's and my y's with my x's. So I'm gonna go ahead and do that, and I'm gonna get x is equal to the square root of y minus 8. Then all I have to do next is to solve for y. So to solve for y, I'm gonna square both sides, and I'm gonna get x squared is equal to y minus 8. Okay, then I'm going to add 8 on both sides, and I'm going to get x squared plus 8 is equal to y. Now, this is an equation. How do I tell, or how do I inform the your teacher that, or the computer, that this is the inverse? I'm going to replace now the y back to a function format, and the function format to represent an inverse is by f to an exponent of a negative 1. This symbol here represents inverse. So again, my answer for this is the inverse of f of x is equal to the square root of x minus 8 is x squared plus 8. Okay. All right. So let's keep on moving forward. It says sketch the graph of the function by applying the leading coefficient test, finding the real zeros of the polynomial, plotting sufficient solution points, and drawing a continuous curve through the points. Okay, so they're giving me a function here, which is um, g of x, and it's negative x squared plus 12x minus 32. So applying the leading coefficient test. So the leading coefficient test says this, um, um, that the leading coefficient of a polynomial can tell us the behavior or the end behavior of a graph. But we also need to know another piece of information. They're asking us for the leading coefficient. So the leading coefficient is related to the degree of the polynomial. The degree of a polynomial is the polynomial or the function in this case that has the highest exponent. So in this case, the highest exponent is the x to the power, the x squared. So this is my leading term, the x squared. So the leading coefficient of my leading term is the value here in front, which is a negative 1. Now, I also need to know, on top of the fact that I needed to know what the leading term was, I also need to know whether this function is an even function or an odd function, and also for me to determine the end behavior of a polynomial or of a function. Okay, so in this particular problem, what I tell my students is here the leading term is or the degree of this polynomial is a 2. 2 is an even number. So since 2 is an even number, this is an even function. And here, um, for to apply my the leading coefficient, okay, it says that if I have a even function and my leading coefficient is a negative, the graph is going to fall on the left and rise on the right. So if I look at the options that I have here, what I want is fall on the left and rise on the right. Okay, so sorry, excuse me, I'm dealing with an even. I'm sorry. When I have my leading coefficients even and I have a negative leading coefficient, it's gonna fall both on the right and fall on the left. Excuse me. So I need to find an equation that's gonna fall on the left and fall on the right. So which one gives me that? That is this one. This third indication, right? The graph of the function falls to the left. Oh no, that one also rises. And then the last one, the graph of the function falls on the left and falls on the right. So the answer is going to be this last one. Okay. So to review what I just covered, okay, I have examples of an even function here, this first two graphs, but the first one has a leading coefficient of a positive number. The second one has a leading coefficient of a negative number. So if you see here, our problem is on the second one. It's an even function with a leading coefficient of a negative. It's going to fall on the right and fall on the left. Yes? So here, this is the graph that is represented for my answer. So hence is the last, oh, it's the last option. Okay? All right. So let's look at this, continue with the same problem to be able to graph. So it says find the real zeros of the polynomial. Okay, so enter your answer as a comma separated list. Okay, so here for me to do this, what I can do is I can use my quadratic equation that we learned in chapter 2 to find the real zeros. And again, when they tell us real zeros, that's just another name for the x-intercepts, is another name for solutions, or roots. So any of these terms mean the same thing, meaning we want to find the x-intercepts or the solutions. Again, the quadratic equation will do that for us. Okay, so um, now, we could have used the quadratic equation, but in this case, um, let's go ahead and factor it. Yes, so um, first I set the equation equal to 0, and then I factor it. I needed to find two numbers that when I multiply them together give me 32. And when I have the same two numbers, I add them, they add up to negative 12. What are those two numbers? A negative 8 and a negative 4. Negative 8 times a negative 4 gives me the um, um, positive 32, and negative 8 with a negative 4 gives me the negative 12. So here it's easy to see that if x is equal to 8, I would get a 0. And if x is equal to 4, I would also get a 0. Okay, so those are my two zeros for this polynomial. Um, now, um, because of the end behavior, I know that it falls on the right, falls on the left. Let's get some more points. Let's find the y-intercept. To find the y-intercept, I'm going to set x equal to 0. So I have here 0 squared is 0. 12 times 0 is 0. 0 minus 32 is minus 32. So the equation of the y-intercept is y equals negative 32. Okay. Oh, excuse me. Give me 1 second. Okay, there we go. Now let me find the vertex of this quadratic. So I'm going to use the formula that, again, we learned in chapter 2, that to find the x value of the vertex, I'm going to find negative b over 2a. In my problem here, okay, a is negative 1, b is 12, and the c is a negative 32. So when I plug these values in here, the b again is a 12, 2a is negative 1, I get x is equal to 6. So that's the x value of the vertex. To get the y value of the vertex, the formula tells me that I just replace this 4 back into my function. So I do this. 6 squared is negative 36. 12 times 6 is 72. So negative 36 minus 72 minus 32 is going to give me the 4. Yes? So the vertex is given by 6, 4. Okay, so let me go ahead and plot all these points. So I plotted um, my zeros at 4, 0, 8, 0. My vertex here was at 6, 4. Again, my graph would go down and would cross at negative 32. Again, and I would do my smooth circle and connecting these dots. Yes? All right. So let's move on to find the rational zeros of the polynomial function. So they give me this function and they want me to find the zeros. Again, they want me to find the solutions of this function. They want me to find the x-intercepts of this function, or they want me to find the roots. Okay, so we don't want to trial and error a lot of numbers. So what we can do is we can minimize the number of values that we can test to find the zeros for by using what's called our rational zero test. And a rational zero test is a way to condense our possibility of numbers that we want to test to find these zeros. Again, because we weren't taught any formula to simplify a cube. There was formulas to find zeros for something that is a square or quadratics, but not for cubes, right? So for the rational zero test, it says that you're going to get the factors of the constant term, which in my case is, and I just want the value of the constant term, which is 9. And I'm going to get the factors of the leading coefficient, which in my case is 1. Okay, and I'm not interested in whether it was positive or negative either of them because I'm going to look at both um, prospects of it, right? So here, the factors of 9 are 1, 3, and 9. The factors of 1 is, well, it's just 1. So to find the possible zeros using the rational zero test, I'm going to look at positive 1 and negative 1. I'm going to look at positive 3, negative 3. I'm looking at positive 9 and negative 1. And then I'm going to look at the factors for the leading coefficient. So I'm going to look at the positive 1 and negative 1. And to find my zeros, I'm going to divide these numbers. And when I do this, I get these are my possible zeros. And again, this is a test. It doesn't mean that it's going to give me all of the zeros or any of them. It's just a test. It's just for us to condense our random pool, right? So we have negative 9, negative 3, negative 1, 1, 3, and 9. So these are possible zeros. Now I know that this function should have at most three zeros because it's a cubic function. At most it should have three zeros, the minimum at least one. Okay, so it could be any of these. So one way to find out if or to find these zeros is now I'm going to use synthetic division. Now that I have some values that I can test, I'm going to use synthetic division. Okay, so first to review synthetic division, we got to make sure that our polynomial is in descending order, which is it is to have a 3, 2, 1 constant, and um, and all of the terms are being represented. There's nothing missing. So to use synthetic division, I am going to only get the coefficients of these terms. Okay, so the first one is a 1, 1, negative 9, negative 9. I'm going to use the first possible term, which is a 1. So to do synthetic division, the first thing you do is you bring down the 1, then you multiply it. 1 times 1 is 1, and then you add these two numbers. 1 plus 1 is 2, and then I repeat again. 1 times 2 is 2. Negative 9 plus 2 is a negative 7. 1 times a negative 7 is a negative 7, and negative 9 with a negative 7 is a negative 16. So the last value here in synthetic division is my remainder. And since my remainder was not zero, one is not a solution or is not an intercept of this graph, of this function. Okay, so let me go ahead and try it one more time. X is not a zero. Okay, so let me try now negative one. I'm gonna go through the same process. Okay, and when I do this, I turned out that um, I do get a zero for this last term. So what this is telling me is that negative one is a zero. Okay, makes us very, very happy. Um, so now what we can do is, since we simplified this cube, when I grab the quotient here, the quotient is this bottom answer here. I have x squared. I lost the degree when I do division. I have x squared. I have 0x minus 9, my constant, okay? And I have simplified, I have something that I can solve for. I can solve a square. Now, this particular one, I don't want to use a quadratic. Let me use my square root property, right? So I'm going to add 9 on both sides, take the square root of both sides, and I find out that the square root of 9 is going to give me plus or minus 3. So they are my three zeros, or I found the three solution points for this graph. Okay, it was a negative 1 from that I discovered from synthetic division, and then from my quotient I have the negative 3 and the positive 3. So these are my zeros. Okay, so now we can graph the polynomial. So let's plot these zeros. Okay, um, these zeros here are indicated as green dots. Okay, using my end behavior, this is the odd polynomial with a leading coefficient of a positive. Says that it's going to fall on the left, rise on the right, and that's how I indicated here in blue. Okay, so I have stuff going in between these. So to get a more accurate graph, we want to pick points that are between these 2 points. So if you notice here, one of the points that I picked was 2. Okay, so 2 is between here, these 2 points here, and then I also picked 1, right? So to tell me a little bit of what the graph is happening. So here, when I picked these values here, when I picked -2, 2, and 1, okay, it gave me these answers. X was -2, Y was 5. Okay, it's right here. When X was 2, Y was -6. It's this point here. And then again, try to do a smooth curve that gives me my graph of this cubic function. Yes. Again, um, so let's go ahead and practice more using synthetic division with complex numbers. So here we have says find the zeros of this function, which is x cubed minus 12x squared plus 52x minus 80. And they tell me that a zero is at 4 plus 2i. This is a complex number because it has a real part and imaginary parts. It's in standard form. That's how we write a standard form of a complex number, real plus imaginary. Okay, so I'm going to use synthetic division to find the zeros. Okay, so again, first you have to check that your polynomial is in descending order and you are not missing any term. And I have a 3, 2, 1 constant. I'm not missing any terms and is in descending order. So let's go ahead and start our synthetic division, bring down our 1, multiply that 1 times 4 plus 2i, add it with a -12. So it's just the real parts that I'm adding. -12 plus 4 is the -8. Multiply the 4 plus 2i, okay, with the -8 plus 2i, I get this value here, -32 plus 8i minus 69 plus I squared. I can combine like terms. 8i minus 16i is a -8i. And I know that 8 of the I squared, excuse me, is a -1 value. So if I replace that, -1 times 4 gives me a -4. Now I have two real parts. -32 with a -4 is let me see, let me go back here. Here we have um, -36i. Excuse me, this doesn't. All right. So, then I'm doing the addition. So we have 60 minus 8i. I'm going to do that again. And I have this value here. Oops, I'm going too fast, clicking too fast. I have this number here. Simplify again. And then add it to the -80. And I end up with 80 again. So 80, -80 with 80 is 0. So um, I find out that 4 plus 2i is a 0 of this polynomial, right? So this is my quotient, okay? Now it still looks a little messy. So what I can do is I can apply my synthetic division again, okay? So now I'm going to use the 4 minus 2i. Again, I'm going to go through this process once more and I end up that this is another 0. But now the quotient is a lot easier to solve. I have x minus 4, so that's easy to see that is equal to 4, right? So the solutions or the zeros for this graph are at x equals 0. The first one that I tried was the 4 plus 2i, which is a complex number. And then I have this one, the 4 minus 2i. So these are my zeros, two of them being complex. Okay. All right. So now let's consider this rational function. Okay, so we have f of x is equal to 1 over x plus 3. They're asking us first A, state the domain of the function. So again, we did this already. To find the domain of a function, especially of a rational function, is a function that has a restriction. And there was three of them that we saw this semester that have restrictions. This is one of them, our rational functions or our fractions, right? The square roots also have a restriction because we don't want negatives inside the square roots or we get complex numbers. And then we also have the logs. We dealt with logs and we cannot put negative numbers for logs. So those three functions will create a restriction. So to find the domain on this particular one, again, just like I did before, I'm going to set the denominator equal to 0 to find out if it has a restriction. Okay, so we have x plus 3 is equal to 0. And when I solve for x, I find out that I do have a restriction. If I were to use x for x -3, I'm going to get a 0 on the bottom, hence I'm going to get an error. So what would be my answer for this? So the answer for this one would be this last line. All real numbers for x except for x equals -3, right? This would be my domain. Again, this would be this answer here. Okay. All right. So now let's go ahead and find our x-intercepts and y-intercepts. Again, to find our x-intercept, we're going to set y equals to 0 and solve for x. So let's go ahead and do that. So I'm going to multiply by x plus 3 on both sides. And when I do this, I get a false statement. 0 is not equal to 1. So by this false statement, this is telling me that this equation, or excuse me, this function does not have any x-intercepts. They don't exist. So that's what I would answer on the computer. It would be D and E. Now to find the y-intercepts, I'm going to set x equal to 0 and solve for y. So when I do this, I am going to simplify and I'm going to get um, y is equal to 1 over 3. So this is my y-intercept in as an ordered pair, 0 and 1/3. Okay, so let's go ahead and find any vertical and horizontal asymptotes. So we technically already found the vertical asymptote. The vertical asymptotes are any restrictions that we would have on our domain, right? So we never want the denominator equal to 0. So that's what we did when we solved for the domain. We found out that x cannot be equal to -3. So what this means is that this is the equation of our vertical asymptote. Now, for the horizontal asymptote. Oh, so the vertical asymptote, we represent that as a dashed line. This on my graph here, they look like dots, but they're dashed lines. Okay, so at x equals -3, I have an imaginary vertical line. Okay, now for my horizontal asymptote, we have a different case. We have different cases that will give us our horizontal asymptote. So we have three cases. So the first case says that if the degree of the numerator is smaller or less than the degree of the denominator, we will always have a horizontal asymptote at y equals 0. That's our first case or our first scenario. We have a second scenario that says that if the degree of the numerator is equal to the degree of the denominator, we have a horizontal asymptote with a ratio. And that ratio is given by the leading coefficient of the numerator divided by the leading coefficient of the denominator. And then the last case or instance that we can have is that if the degree of the numerator is larger or greater than the degree of the denominator, then there's no horizontal asymptote. But what happens with this last situation is we don't have a horizontal asymptote, but what we end up having is what's called a slant asymptote in this case. Okay, so let's look at the problem that we have in hand. Here, what we can see is the degree of the numerator here is 0, right? Because I can write here as a value x to the 0. X to the 0 is always 1. Here, the leading coefficient is 1. So 0 is smaller than 1. So again, the degree of the numerator is smaller than the degree of the denominator. So I'm going to have a horizontal asymptote at y equals 0, as represented here in blue as a dashed line. Okay, so now let's go ahead and plug in some stuff that we know. Okay, we know that it's not crossing the x-axis, but we have our y-intercept, we have a vertical and a horizontal asymptotes. So let's get some additional points so we can do our smooth curve. Okay, so again, this is my vertical asymptote. Let me pick an additional point, x equals -2 and x equals 2. Okay, I'm also going to pick x equals -4 and x equals -5. Okay, so when I solve for these points and plug them in, I'll do my smooth curve, but I'll let the computer do the work this time instead of a squiggly line. You see I have a smooth curve here. This curve connecting the dots on the left of the vertical asymptote will come close to my vertical asymptote, never cross it, never touch it. And then it's going to pick up again when it jumps to the other side. It's very close to this line, didn't cross it, didn't touch it, connect my points, and then I reaching my other horizontal asymptote that you can see it's my x-axis. My graph does not have an x-intercept. It's never going to cross the x-axis. It's going to get very, very close to this line. Yes? Okay. All right. So again, usually on for your options on WebAssign, they ask you to pick the right graph. Again, and you can see from our graphs, um, the one that matches is this first one. All these have the wrong vertical asymptotes. This one had the right vertical asymptote, but it's telling me that I have an x-intercept. No, my graph did not have an x-intercept. So, and then the points that I had were on the left of the vertical asymptote. Yes. So excellent. Um, let's move on. All right. Oh, this was one of my favorites. It says use properties of logs to expand the expression as sum, differences, and or constant multiples of logarithms. Okay. So for this particular problem, we have a log of base 5, and into this log we have something that's being divided inside. We have the square root of x squared minus 9 divided by 4. So to use my properties, this is a quotient rule that says that when I have a log that I have two things that are being divided with each other, what I'm going to do is I'm going to subtract the um, the numerator with the denominator. So here, applying the quotient rule, I'm going to get the log of base 5 of the square root of x squared minus 9 minus the log of base 5 of 4. Okay. Now, can I convert these into powers? So the answer is yes. The first one, the square root, can be represented as an exponent. That is 1/2. Okay. So since I have an exponent, okay, I can use what's called my power rule. And my power rule says that when I have an exponent to an value in my log, this exponent is going to be multiplied to the log. Now, again, we kind of skipped it because the 4 I could have written that as a square as well. So, but we'll just leave it for right now. Okay, so applying my power rule, I'm going to multiply the 1/2 to my log, and I brought it down, right? So I have 1/2 log of base 5 of x squared minus 9 minus the log of base 5 of 4. Okay, now I didn't mention this, but again, when it says to expand, they want me to make it into multiple logs, not just one log, so multiple. So if you see here, I have two logs. I went from one log to two logs, but I haven't finished. Okay, this x squared minus 9, I see that this is a perfect square or a difference of squares, right? I can factor this to this x squared minus 3 squared, which can be as a product of x minus 3 times x plus 3. Yes? So I have two things that are being multiplied to a given log of base 5. So I'm going to apply my product rule. And my product rule says that when you have two things that are being multiplied into a log, you can expand it by adding the two logs together. So I have here 1/2 log of base 5 of x minus 3 plus 1/2 log of base 5 of x plus 3 minus the log of base 5 of 4. And if you see, I went from one log to three logs. I expanded my log to multiples, and all of my values have a constant term. I don't have any power rules. I don't have any squares or cubes or anything like that. Okay. All right. Let's do the opposite now. Instead of expanding, let's condense. And we're going to use our properties of logs to also do this process. Okay, so let's start with the A. So if you see here, the A, I have three logs. Okay, now in order for us to use our properties, you got to make sure that I am dealing with all the same base log. If any of them have different bases, then I cannot condense because I cannot apply my properties. The properties only apply to a single base. Okay, so first I have to follow kind of order of operations. I have to see that if I have any numbers that are being multiplied to the log, and if I do, that means that these are exponents. This is power rule. So if I see I have two of them that I do have something multiplied, I had a 6 being multiplied to this log, so this 6 becomes an exponent to the y. I had a 7 being multiplied to this log, so that means that this 7 becomes an exponent to the z. So this was using my power rule for logs. Okay, now I have nothing that is being multiplied, so I just have additions and subtractions. So I'm just gonna go from left to right. Okay, just gonna go in order. So the first two things that I see here have a log of x minus a log of y to the sixth power. To combine these, I'm gonna use my quotient rule that says when you have two logs that are being subtracted from each other, you divide the inputs, right? So I'm going to have the log of base 10. That's another thing. I know that these are the same logs. When they don't write a subscript here, when you don't see a subscript number, that means that I'm dealing all with base 10. Okay, so I have a log of base 10 of x divided by y over 6 plus log of base 10 z to 7. I have two logs that are being added with each other. Now, this is the product rule for um, logs that says that when I have two logs that are being added, I'm going to multiply their input values. Okay, so here we have log of x divided by y to the sixth power times z to the seventh. To simplify it, to make it a little bit prettier, okay, let's go ahead and multiply those two together. The numerator, the x times the z to the 7, is going to give me my final answer divided by y to the 6. Okay. Um, so if you saw, I went from three logs to one log. Okay. Um, just for time purposes, since I only have 8 minutes, let's go ahead and try different ones using natural logs, right? So on solving. Okay. So let's solve for these equations, and the problem says approximate results to three decimal places. So let's do A. So for A, the first thing that I want to do is I want to apply my quotient rule to condense the problem, to make my life easy. So I have a natural log of x minus the natural log of x plus 6. This means that I can condense this to a single log. This is natural log of x divided by x plus 6 is equal to 7. So what I can do to solve for this is I'm going to change it into its exponential form. And I like to do this also to practice this, to practice converting from log to exponents, which these are inverses of each other. Okay, so here the inverse of a natural log is an exponent with the natural e. Okay, so here the output of the log is the exponent of my exponential, which is e to the 7. The input of the log is the output of the exponent, which is equal to x over x plus 6. So the next thing I need to do is multiply x plus 6 on both sides, okay, and distribute the e to the 7. So when I do that, I get e to the 7x plus e to the 7. E to the 7 times 6 is equal to x. I want to solve for x, so I'm going to combine the x's together. So I'm going to move the x to the left side. Anything that does not have an x, I'm going to move it to the right. It's a term. Now, I don't want to put it into my calculator yet because I don't want to be dealing with all these decimals, right? So right now, I'm just going to leave it with the information, okay? So let's go ahead and gather the x's, and I'm going to isolate the x by factoring out an x, okay? So when I do that, I factor out x, I'm going to get e to the 7 minus 1 is equal to minus e to the 7 times 6. To solve for x, I'm going to divide both sides by e to the 7 minus 1. Okay. And I have this. X is equal to negative e to the 7 times 6 divided by e to the 7 minus 1. Now I'm just going to bring my calculator and just solve it. Okay. And again, I have a snippet of my TI here, TI-83. Um, um, I like to put it on here so you can see all the parentheses that I have to use in order for me to solve it, because again, I have to tell the calculator what to do. I have to tell it to follow order of operations. Calculators don't know order of operations. So again, I have to tell it what to do. So when I plug it in, I have here my answer, but the problem said to round to 3 decimal places. So the way I do that is I go to the third decimal place, which is a 5, and then I look at the number to the right of that. Since that number is less than 5, that 5 is going to remain the same. If that number would have been 5 or greater, I would have added one value to that 5. So that wasn't the case. So the answer here is negative 6.005. Okay. All right. I have 5 minutes. I think I have time for one more. But again, you want to check your answer. Okay. And remember, we cannot, this was the other case that we cannot have negatives for logs that I had mentioned to you. So if I were to put this negative value into this, I would get an error. So this particular problem, we did all this work, and I know some of you guys are going to complain. The answer is no solution for this one because again, we ended up with a negative value and we cannot have negatives for logs. It's one of our restrictions. Okay. All right. So let's do this. Let me run through this one quickly, which is the same way. Again, we're condensing the right side. Um, on this particular one, this one's different, and let me go ahead and talk about it. You see that I have two logs that are equal to each other. They're natural logs. So the best way to solve for this one is using my one-to-one property. And the one-to-one property says this, that when you have two logs that are equal to each other, for them to be equal to, for it to give me a true statement, the inputs have to be equal to each other. So that's what I did. I grabbed the inputs. I grabbed x plus 9 should be equal to the x minus 6 over x plus 6. And then it just becomes the algebra solving for x again. And as you see here, once I moved all my x's to the one side, I have a quadratic. You can use quadratic, you can factor. Again, in this case, I use a quadratic to solve my solution. And I end up with a complex number that says that I have negatives. So again, there is no solution for this one either. Okay. Um, so I can do this very last one. Okay, so we have log of x minus log of 9, x minus 8. I need to solve. Again, the first thing I'm going to apply the left side by my quotient property to condense those two logs. So I have log of base 9 x divided by x minus 8. Condense those two logs. So I have log of base 9 x divided by x minus 8. And again, I'm going to change it to its exponential form. The base of this log is 9, so that's the base of my exponent. The input of the log is the output of the exponent, and the output of the log is the input of the exponent. It becomes the exponent. So 9 to the 1/2 is the square root of 9, which I know is plus or minus 3. And if I solve for x, I have two solutions. I have x is equal to 12 and x is equal to 6. And then again, you want to test these two values to see if it gives you um, a true statement. So again, thank you for joining me today on our last Happy Math Hour for the semester. I wish you the best of luck. I know all of you will do great. Okay, so again, I will pass it now to our presenters. And again, good luck on finals and have a Merry Christmas. Goodbye, all.
Thank you, Mr. Carizales, for your presentation. We do want to remind everybody about our previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist later today. Also linked was a short survey to help us improve our TVE sessions. So if you guys could please take a few minutes to fill out that survey. And before you all leave, I want to share our last TVE session for the semester. Give me just a second while I go ahead and pull this up real quick. There you go. So at 1 p.m. today in this room, we will have a presentation on how to improve your credit score with Enrique Lechuga. Thank you all for coming in today for our last Happy Math Hour of 2024. We hope you all have a lovely weekend, and the TVE team wants to wish you all good luck on your finals. If anyone has any questions, feel free to use the chat box or your mic, and we hope everyone has a restful winter break, and we hope to see everyone again next semester in spring 2025 for more of our TVEs.